AP Stats, what a do. It's 8 o'clock tonight, and it is on a Monday night. I mean, can it get any better? You've got an AP Stats study session. Oh, I love doing this. This is one of my favorite things to do within the week. And so buckle up, fasten up, whatever you want to do, and let's get rolling. I wanted to bring a little guest with me, mainly because many of you have not seen him yet. And so here's Bennett. Let's see if we can get him here. Oh, there he is. Say hi. He's not really, he's kind of awake. He's just sleeping on the floor. Look at him. Oh, gotta love it. Love being a dad. Hey, again, I see we have 5 viewers tonight. I'm really stoked, really pumped up. Go ahead. I just saw you, Lynn. Yeah. That's my wife. Right there. Right there. She's trying to be sneaky. Hope all's well. We're starting off with some fun times. Go ahead and go ahead and take that out, and we'll go ahead through the review. Sorry, that was probably one of the funniest things I've seen. Go ahead again. We're gonna go to our review. Feel free to post some questions on the YouTube help link there. I've seen. Go ahead again. We're gonna go, and I'm gonna pause this with my voice right there. And I see the chat. Let's show the chat here. And perfect. Yeah, it's pretty funny. That's pretty funny right there. Lindsay, you're a hit right now. Just so you know, you're a hit on this. So go ahead and throw some questions out there. And I think Ryan's the top one that I see. I don't know if that's. Let me try to reload that just in case. Throw this up, and then we'll look at some questions. Feel free to throw the any questions you have out there. I'm gonna make sure. I'm just gonna make sure that it's coming up. Perfect. Okay. Yeah. Okay. So the first thing I want to do is go through the concept list real fast. And basically the idea of this is just going through any questions that you may have over the specific topics. So let's look at this one. I'll just kind of go step by step through, and I'm just going to make little notes here off to the side, and hopefully that will be of help to us. Number one, understanding statistic, a parameter, a sample, and a population. Know how to apply these definitions. Well, couple things. First of all, we know that a statistic is something that estimates a parameter. You say, Coach, what are you talking about? Well, remember when we talk about a statistic, these are values. These are numbers that describe various things. For instance, a statistic is a number that represents a sample, right? And a parameter is a number that describes a population. The big thing to remember on this is, let's say we're talking about all of GAC as our population, that 43% of individuals at GAC own AirPods. Well, then we take a random sample of that population, let's say 10 students, and in that we find that 30% of that sample own AirPods. We see in that instance that the 30% is the statistic because it's taken from my sample, whereas the 42% is the parameter because it's taken from my population. So that's the difference there. Okay. Number two, calculating sampling distributions of mean and proportions. Calculate sampling distributions of means. So I would say here, understanding the different formulas. For instance, mu of X bar. This is mean world, right? Because the X bar. The mean of a sampling distribution of X bar is equal to its true mu, right? Almost said mu, by the way. And the proportion world, this is going to be a fun podcast. I already can tell. The mean of p hat is equal to my parameter p, right? Let's talk about the standard deviation formula. That is for the mean. Again, this is on your sheet, just a heads up. But it's the standard deviation of the population divided by square root of n. And for the p hat world, it is the square root of p times 1 minus p all over n, right? Now, the key of this is, and I know I'm kind of going off track here, with both of these formulas, in order to use this, we have to show independence or 10% condition, which states that little n is less than or equal to 1/10 of my population of n. Remember that little n is my sample size, right? So these are just some things that I have to do. Again, I have to show this in order to use the standard deviation formula, which comes back to number 4, okay? Remember, it's independence. Independence is the reason why I have to show this. If it's not independent, we can show that it's so large that if it is so large that, you know, it doesn't matter, the fact that you didn't replace it or that it's not independent. All right, law of large numbers. Now, remember, we have this thing where we have to see, is my sampling distribution normal or not? Remember, with my proportion world, p hat, versus my mean, x bar, there's two different things. With p hat, we do the law of large numbers, which states that n times p and n times 1 minus p is both greater than or equal to 10. Now, with x bar world, a little different. Condition 1 is the population normal? That's the question. Condition 2, if it is not, then we have to go to the central limit theorem, which states that n is greater than or equal to 30, which means my sample size is greater than or equal to 30. Only one of these conditions needs to be met, but I always start with number 1 and then gradually move to number 2 there. Okay. Cool. Let's see here. Let's go to the next one, number 5, mean and standard deviation. We already did number 5 there. Number 6, using numbers 3 to 5 to show a normal distribution and the probability for a given condition. Oh yeah. Number 6 is the FRQ that we're going to look at. The one that we were focused on today in class is a really good one. There's also another one that we did, I think it was on Friday, when we really focused on the mean world, but know the difference between the two and how do I show normality within each. And really just, I'm telling you, you're going to need to know it. Huge part of it is dissecting the formulas for proportion world and mean world. And again, I have that with that sheet that I've given to you on the front of 7.3 notes. Number 7, know the statistically significant rule of 5% and know how to develop a conclusion. All right, well, this is pretty good. We look to the 5% rule that if something is, let's just say X is greater than, forget the less than, or forget the equal to, greater than 5%, we say we literally will start it this way. We do not have, I would say, okay, backing up. Let me see if this will help. Hopefully this will help. 5%. So because my value, and you could actually plug that in, is greater than 5%, we do not have convincing evidence to say ... whatever we're saying in context. If we are saying that it is less than 5%, we'd say since X is less than or equal to 5%, we have convincing evidence to say that ... put a little context in there. So this is, again, just something from number 7 that's important, of knowing if something is less than 5% versus something that is greater than 5%. Remember the thing today in class where we had 9 of 25 were orange, which gave us a proportion of 0.36. Be careful, because this is talking about my p hat value. To find the 5% rule, we use that normal distribution, and we're asking ourselves that when we highlight it, if we're talking less than, obviously if it's greater than, it'd be highlighted over here. But if I highlighted anything less than this value, then this is what I would shade. And we're looking to see, is this 5% or less? That's the idea. Central limit theorem and knowing how to apply it. We already went through that. How does an increase in sample size impact bias and variability? Well, if I were to increase my sample size from 10, okay, so let's say n was equal to 10 versus n is equal to 20, 20 would have a lower variability. However, this would not decrease bias, right? Increasing sample size does not decrease bias. How I sample is how I decrease that bias. So if I want to lower variability, I can increase my sample size. That's what it's referring to. Okay, no specifics of a sampling distribution. It's a sample of all possible samples within a population of size whatever, right? So if I'm sampling 20, it's a sample of size, or all possible samples of size 20 from my population. Now that's impossible a lot of times, but that's still technically the definition there. Number 11, this is the law of large numbers, which tells me that n times p and n times 1 minus p are greater than or equal to 10. We need to know this, know how to apply it, and then also make sure that you understand how to know that it approximates something as normal for sampling distributions for proportions. Number 12, standard deviation of a sampling distribution for proportions. Okay. Remember, it's got to use the 10% condition. Okay. And then again, that's the formula. Number 13, changing sample size and how it impacts the standard deviation. Just like we said, the higher the sample size, the lower the variability, which would also decrease my standard deviation, right? Because standard deviation is a form of variability, okay? Okay, 14, conditions for a normal distribution or X bar of a sampling. Okay, well, a lot of normal distributions. Have you known this? Have you seen this here? Number 1, is the population distribution normal? That's question 1. If it is not, we go to condition 2, which is CLT, which states n is greater than or equal to 30, which is our sample size. And if neither are right, we cannot assume normality. Number 15, definition of bias as it relates to the true mean and the sampling distribution mean. Well, remember that a sampling distribution is unbiased if the mu, I'm using proportions, of p hat is equal to mu, right? So is the true mean, the true parameter, I'm sorry, this should be p, my apology, is the true parameter of p equal to the sampling distribution for sample proportions, right? And 16, what happens when you increase the sample size of a sample? Man, there's a lot of those, I guess. Just make sure you look over that, look through it. And the big thing is prepare, prepare, prepare. My 5 P's, proper preparation prevents poor performance. And that's exactly what you're doing tonight. I appreciate you being here tonight and appreciate all your help. I am stoked to get to your questions, all right? Hello, Brianna. I'm starting with your question. Well, not your question, just your statement. Sampling distributions of sample proportions, we can do that. 70% broke. Hey, Coach, what's up? What's up, Eric? Let's go to Lindsay's, and I'm going to continue to go from, yeah, Eric, where are the FRQs? So I will actually scroll through them, but they are on like the bottom of the sheet there. If you go to these, let me go here. Here they are. If you want to choose 2 of these, this is number 1. Number 2. Okay. Number 3. I'm looking for a good one, Lindsay, while we go through it. Number 4. Number 5 and 6. There's 6. You just need to choose 2 of them. That's really all you need in this. That's number 7. Okay. That's a good sample mean one if you're looking for that one, that FRQ there. Looking for one that would be, I think that's the answer, so that wouldn't be it. Trying to see here. I'll get to, I think Michael and Jacqueline and Shane did this one here, and so we could start on this one. I know we did this one today in class. I know Lindsay said she needed some help on this one. So let's just identify a couple things, okay? How would I approach this FRQ? Imagine a very large candy machine filled with 3 types of candies. The company says that 45% of the candies in the machine are orange. This is automatically my population. So I could just say that this is my true P, okay? Assume for the moment that this claim is true and that the machine has just been filled. When you insert money, you get 25 candies. Let P hat be the proportion from the sample. Yeah, so as we look at this, we understand that the mean of my sampling distribution is mu of P hat equals P, right? This is on your formula sheet, but this is in fact true. That if I were to take a true sampling distribution, that the mean of that would actually equal the true mean of my population, or true proportion of my population, which in this case would be 0.45. Okay, check, check. Second thing, find the standard deviation of the sampling distribution of P hat, which states that sigma of P hat equals square root of 1, or P times 1 minus P all over N. And in order to show this, we've got to show our 10% condition, okay? And what I would do is just show N is less than or equal to 1/10 of big N by plugging values in. And like right here, this would be 25. And I know I'm running out of room, but 25 is less than or equal to 1/10 of all candies in the machine. We know this to be, in fact, true. And so because of that, we would say that we can go ahead forward with the standard deviation formula here. So we would plug in square root 0.45 times 0.55 divided by 25. And I believe we got approximately 0.099, something like that. And that's how we would find it. Now, part C, explain why we would use, why it would be appropriate to use a normal distribution. Because it's P hat world, we don't go to the 10% condition or the CLT, but we have the law of large numbers, which states that N times P is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10 too. So what I'll do is I'll plug these in, show it, and then if it's true, then both would come back true, that they are greater than or equal to 10, and then allows me on part D to use that normal approximation. Okay. Again, for sampling distribution, you want to make sure that you show it, right? So you want to show that the normal distribution, the law of large numbers, is true. That way we can go ahead to the bottom part. So now we've got our mean, which is 0.45, our standard deviation, 0.099. So here we go. And then it says that is less than or equal to 0.36. So here's 0.36. And we're finding this area. Now you could do z-score. A lot of people do, where we do the z is equal to value minus mean divided by standard deviation. That's appropriate. Another way to kind of write this is to do our normal CDF with putting the formula in first. So we got lower, comma, upper, comma, mean, comma, standard deviation right there. Okay. Cool, cool. So now, sorry, I'm going to lay down here. Get you there. Hope you're having a good day today, by the way. I had a Gucci day. I was finessing all day today. That's right. Eric, I got some clout, though. We're good. What was that phrase that I said? It was something that you liked, Eric. I forgot what it was. Anyway, we'll remember it later. But once I plug in these values, I remember it was 0.1814, which means that 18.1 18.14% is this area, okay? Now I'm almost done, and again, I'm just kind of going through this quickly. We know it says if your sample actually contained 9 orange candies out of my 25, which means 9 of 25, which would be the same proportion as what was above. Would that make you suspect that the company isn't putting enough orange candies in this machine, or could it have happened purely by chance? Again, because of the fact that we can go back up here, we're really saying what is this area, is that statistically significant? Because it matches the same, right? Now, this does not have to be less than or equal to 5%. It's really this. So we would say because 18.14% is not less than 5%, we do not have convincing evidence. Convincing evidence to ... and I'll just kind of, instead of writing it, to suspect that the company isn't putting enough orange candies in the machine. You just basically restate right there, okay? And that's how you attack it. Lindsay, I hope that helped. Hope that helped there for you. Hope that did help you. All right, let's go to the next one. All right, Lindsay, we got yours where the FRQs did that. It says ultimate FRQs. Yes, that's it, Ryan. Nicely done. Wait, can you review difference from parameter and statistic? Yeah, Brianna, we can do that. Let me go, and I'm just going in order, y'all. So y'all are probably throwing shade on me right now. My apology. Yep, there's shade. That's okay. I'll come back to that shade and I'll address it. It's okay. Although I did give Brianna a hard time today, which I really do apologize for that, Brianna. That was inappropriate. All right, so let's go to this. Where are you? Oh, yeah, you know what? I'll just pick up right here. I'll kind of clear this out. So remember this, that a statistic estimates a parameter. You say, Coach, why'd you put that arrow there? I want to show you something. We remember a statistic as being X bar, P hat, S of X. These are all samples, right? So, but the actual number itself we call a statistic. Now, what happens is they estimate specific things in a parameter. For instance, X bar estimates mu. A lot of times we don't know mu because it's like the true population, and the population becomes so big it becomes tough. P is the true proportion. So we take a P hat sample and estimate P. And S of X is related with sigma. Sigma's population. Standard deviation of the sample is S of X. So that would be the difference between the two. And so the sample is the actual people or subjects or individuals, whereas the actual number themselves are called statistics. I hope that made sense. If it doesn't, keep throwing stuff out there. Yeah, Eric, just choose 2 of them. That's perfect. Thank you, Ryan. Ryan, you're helping out a lot. Perfect, Brown. I see. Can I go over an FRQ? We need one in the mean world. Yeah, Ryan, if you want to see your 7.1, 7.2 test, I think I still have them. I think. Okay, don't quote me on that. I believe we still do. So if you needed some stuff on that, you could. I should have given those earlier. I apologize. But if you want to see them in the morning, that'd be good. Good. Brianna, do you see that? Perfect. Ryan, you're saving lives today. Mean world. Eric. Oh, man, there's some shade being thrown right here between Brianna and Eric. Oh, my goodness. Oh, my word. Oh, man. Okay. Did I invent comedy? I think I might have. Okay, I'm going down. This is all the I didn't forget about your mean FRQ. I just can't help. Psych. Oh, he's not sorry. Don't be fooled. Brianna, you're making Coach J feel bad. You're stinky. Wow. That really went somewhere. All right, very good. Oh man, this is getting intriguing. Wow, this escalated in a hurry. Wow, I don't even know. I might want to stay away from that. All right, here we go. Let's as we keep going here. My apology. I was seeing where we were at. Let's go to the mean world. You're a mean one, Mr. Grinch. You really are. Neil, you're slumming it out of the cactus. Something like that. Okay. Okay, I'm trying to see if this one would be good. Oh, this is Gucci. Okay. Making sure this one's one that... Okay, let's do this thing. Buckle up tight, fellas and ladies. Let's get this underway. All right, number one, trains carry bauxite from a mine, northern New York State. Filling equipment is used to load ore into the hopper car. When functioning properly, the actual weights of ore loaded into each car by the filling equipment of the mine are approximately normally distributed, which is nice because that's the population. With a mean of 70, standard deviation of 0.9. So let's talk about this. First of all, we know the population is normal. It's huge. Mu is equal to 70, and the standard deviation is equal to 0.9. Notice I do not have subscripts because this refers to my population, okay? If the mean is greater than 70, the loading mechanism is overfilling. Okay, fair. If the filling equipment is functioning properly, what is the probability that the weight of the ore in a randomly selected car will be 70.7? All right. Well, we could look at this. We know it's normally a normal approximation. It's a randomly selected car, so this is not a sampling distribution for part A. So what we're going to do here is we're going to say, okay, this is 70. We can even do like 70, 0.9. And we can do that there. 70.7 or more would be over here. So this would be 70.7 or more. Okay. Now we could do a z-score by doing z equals value minus mean, right? Minus mean divided by standard deviation. And if I were to do that, the value would actually be 70.7 minus 70 divided by 0.9. And if I were to do that, see here, get my calculator out. Do y'all have a phone calculator? I love my phone calculators. Y'all should get one. Be good stuff. 0.78. So 0.78 is I would just actually do 0.778. Oh, or 0.78 is fine. We'll go back to table A, which I'm going to do now. Beautiful like diamonds in the sky tonight. All right, I'm getting it here. Let's see. 0.78 to the right. Okay, 0.7. I got 78.23. So that would be anything to the left. Remember that. So 78.23%. So 1 minus 78.23 is the actual percentage. So I'm going to do that. 1 minus is, hold up, I'm sorry. 1 minus 0.7823 is 21.77%. Or we could just say 0.2177. Okay. And it doesn't say right in context. If you want to, especially if you have time, just write a little context there. Probability that the weight of the ore of a single randomly selected car will be 70.7 or greater. Okay, that's what we put there. Just restating what it says on that side. Part B. Suppose that the weight of an ore in a randomly selected car is 70.7 in A. Would that fact make you suspect that the loading mechanism is overfilling the cars? I would say that, so it says suppose that the weight of ore in a randomly selected car is 70.7. Would that, I would say that this would be no. No, it wouldn't. First of all, there's a couple things. Number one, It's one randomly selected car, and since, and this is where we go 5%, right? Make you suspect, since 21.77% is greater than 5%, we do not have convincing evidence, right? I'm not going to keep writing this, but we do not have convincing, maybe I will keep writing, I'm feeling it, evidence, ... and again, don't write ... but actually say convincing evidence that we suspect the loading mechanism overfilling the cars. You know what I mean? All right, so then we go to the next one. Part 2. Part 2 says if the filling equipment is functioning properly, what is the probability that a random sample of 10 cars will have a mean weight of 70.7? All right, so coming back here. First off, this is a sampling distribution because we have 10, right? So I'm going to actually flow this out, all right? So we're going to say mu of x bar equals mu. Sigma of x bar equals sigma over square root of n. I showed well, let me plug this in. This would be 70, right? If I plug this in, this would be 0.9 divided by the square root of 10. But in order to use this, I've got to show my 10% condition, where little n represents the sample size of greater than or equal to 1/10 of big N, where big N would be, I could replace this with all train cars. I'm going to assume this to be true. Okay, so we're good there. Then we go to, we'll go to the next one right here. And since this is true, we can go ahead to the standard deviation. We recognize that we go 0.9 divided by the square root of 10. We get 0.28, 0.285 right here. Because it's true, I can use it. So we got step 1. Step 2, standard deviation. We're good there. Can we approximate this as normal? Yes. Yes, we can approximate as normal. Since the population is normal. Okay. So we're good there. We then come on this side. We got a normal distribution. So we've got this here. We've got 70 right in the middle. And sorry, I'm getting text right now. 70.7 or greater than would be over here on this side, right? Same idea. The only difference with this one is the standard deviation, which has gone to 0.285. It's decreased. So now I'm going to do normal CDF just to show you that I could do this if I wanted to. Normal CDF, lower, comma upper, comma mean, comma standard deviation. And so then I'm going to actually like plug this in, right? So normal CDF, lower is my 70.7, higher is 99999. Mean is 70, standard deviation is 0.285. So we're good here. So I'm going to go second. Normal CDF, 70.7, comma, 99999, comma, 70, comma, 0.285. And when you do that, you get 0.00, approximate 0.007, which, by the way, is 0.7%. Okay, so this is like 0.7%, I could say. Now, coming back to D, this is much different than what we said in part B. We could say, yes, we are, would you suspect the loading mechanism was overfilling the cars? Yes, I would say since our value, 0.7%, is less than 5%, we do have convincing evidence to suspect that the loading cars are overloading the, or the mechanisms overfilling the cars. And you could say something about it being statistically significant, but that's how I would say it, because it's less than 5%. We do have convincing evidence, and then to say, blah, blah, yada, yada, yada. Okay, cool. All right, man, that was a good one. Man, we just rocked it, y'all. We just rocked it. By the way, y'all should feel loved. I'm missing The Bachelor for you. You know what I mean? Missing it for you. I'm joking. All righty. Eric, I'm blocking you. Christmas is over. Finally, bye. Okay. Fight in the quad. Okay, now. No, well, I can't say that. Would we do normal CDF? Yeah, we could do normal CDF, Brianna, for sure. I did Z-score. You could do either or. Just make sure you write down the formula. There you go, Eric. I got you. Gotta love it. Gotta love it. All right, let's see here. What we got? What else we got going on? All right, any multiple choice that y'all saw? I think Jade, I don't know if Jaden's in the house. I don't mean to throw her out there. I don't know if she's in the house, but she did say she had some questions. So I don't know if y'all have any questions in regards to that. Multiple choice sections. Feel free to throw those out there as well. I thought we did some good stuff on that. I thought it was some good things. Let's see here. Okay. We could go through like number one. Newspaper poll reported that 73% of respondents, okay, it's kind of the big kind of highlight of this is the respondents part, right? 73%, like business tycoon Donald Trump, the number 73%. Well, that's not the population, right? It's respondents. So it's not a sample. The sample is those who responded. The actual number in and of itself is a statistic, okay? So make sure of that. That's kind of the big part that you need to focus in on. The name for the pattern of values that a statistic takes when we sample repeatedly from the same population is a sampling distribution. It should be. Okay. Cool. Yeah, we'll do some multiple choice here. That's perfect. Gotcha, Brianna. If we take a sample of size 500 from a population of size 5 million, the variability of our estimate will be what? Well, the higher. Okay. Well, we're talking about the variability, right? Where n is equal to 500. So simple random sample of size 500 from a population. I'm trying to think. As I look at it here, the variability does not change as the sample size. Like this, it's all about the sample size. I do not care about big N, right? Think about it. Like when I look at my sigma of p hat, it's equal to the square root of p times 1 minus p all over n, right? Or of the sample mean, sampling distribution for sample means, this is the sigma over square root of n. It has nothing to do with my big N, has everything to do with my little n. So we would say it's about the same. To be C, it's about the same. It has no bearing. Notice the 500 being the same here. The sample size is the same. Therefore, the variability would be the same in that too. Here we go. All right, number 4, increasing the sample size of an opinion poll will reduce the bias. No, can't. It's not reducing bias, okay? We reduce bias by sampling better. We have a better sample. We have a better representation of our population. And it has nothing to do with sample size. Sample size, all that does is reduce variability, okay? Reduce the effect of non-response in the poll, no. Reduce the variability of the poll result. Yeah, that's what we would get. Reduce the variability of opinions. No, that's not. Won't reduce that. It'll reduce the variability of the poll results. That's what we would be getting there. Number 5, the sampling distribution of p hat has a mean of, well, mu of p hat is equal to p, right? What is the p? That's the question. 30% of all, again, of all Division I athletes. So p would be 0.3, right? Because that's where we're at. So the mu of p hat is the sampling distribution of sample proportions. So that would be b, 0.3. It's the same. Standard deviation, you got to check to make sure that the 10% condition is true, which I believe it does pass. So just make sure that it does pass there, and then you can go ahead and do sigma p hat equals p times 1 minus p all over n. Cool. So we plug that in, and what do we get? C. C is what we get. C there. Okay. All right. Decreasing the sample size. Oh, this one's a good one. It's a good one. Decreasing the sample size from 750 to 375 would multiply the standard deviation by what? Well, let's put both of them here. Simply see what we would have here. So we would have 0.3 times 0.7 divided by 750. Okay. And over here it would be the same thing. The only difference would be that we would actually be having 375. So if I decrease the sample size, how do I get from here to here? Well, if I'm trying to get multiplied. Okay, so if I were to plug this in, you know what I would do? I'll just plug both of these in here and then just try to get it out. My big thing is I want to get from here over here, meaning I want 375 to be 750. So I can't just multiply by 2 because that won't work. Can't multiply by square root of 2 or even 1/2 because the 2 can't get in the square root. It's actually 1 over square root of 2. Because if we did 1 over square root of 2, square root of 2 times square root of 375, and then obviously the top stays the same, we'll then change the bottom to square root of 750, and the top stays the same, which is 0.3 times 0.7, which is the same as over here. So I would just say the answer would be 1 over square root of 2. You could also plug those both in your calculator and then just see what what I could multiply by to get to equal the other. Okay. All right, let me pause for a second. Let's check it out. Multiple choice. How do you spell it? Charles is here. Welcome, Charles. Hopefully, hop right in. Pause and rewind and ask questions however you want to, my man. We're just going through a lot of the multiple choice right now. If you want that. Oh, the sampling distribution. These are all so good. The sampling distribution of p hat is approximately normal because, well, remember p hat world. This is just stuff you need to know. Law of large counts, which states that n times p is greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10. So it would be B. It would be B. Hold up. Yeah, I think that this is what it would equal if I plugged it in. So yeah, should be B. Good. Just looking at different things here. A newborn baby has an extremely low ELBW if it weighs less than 1,000 grams. Study of the health of such children in later years examined a random sample of 219 children. Their mean weight at birth was 810 grams. Sample mean is an unbiased estimator of the mean weight of all, which means that, well, this would just be the definition. In all possible samples of size 219 from this population, values of X will have a distribution that is close to normal. No, unbiased means mean of the values of X will equal that. That's it. That's it. B. So it's B. Remember, the means of the values of X bar will be equal to mu, right? Because that's the definition of unbiased, right? That the mean of the values of X will equal mu. Okay. Just going through some. Again, give me some more questions if you've got any more. Tomorrow, I am going to be there tomorrow, by the way. Yeah, increasing from 1,500 to 4,000 has no effect on bias, right? Increase or decrease in the sample size, no effect on bias, but it will reduce the variability of the estimate. Reduce. Increased sample size reduces variability. Okay. Good stuff. Okay. Suppose we select. So this, okay, so let p hat be the proportion of successes in the sample for which value of p hat would, well, again, this would be n times p is greater than or equal to 10. N times 1 minus p is greater than or equal to 10. And so n would be 100, right? So we'd say 100 times p is greater than or equal to 10. And 100 times 1 minus p is greater than or equal to 10. I would just, in this instance, just plug in values, A, B, C, D, E, plug in the values for p, and see, do they really, are they really greater than or equal to 10 there? Okay. Cool. Yeah, okay, so 816 is a good one. 16 says the central limit theorem is important because it allows us to use the normal distribution to make inference concerning the population. If the sample size is reasonably large for any population, if the population is normally distributed and the sample size is reasonably large, if the population is normally distributed. Now, this is true. C is true for means, but that is not called the central limit theorem. We show first this part, C, but then if it's not true, we do the CLT, right? So notice D is not correct if population size is reasonably large. Has nothing to do with population, right? CLT states that n is greater than or equal to 30. So if the sample size is reasonably large for any population, if the population is normally distributed and the sample size is reasonably large. No, it doesn't have to have both. It just needs to have one of them. And that's why A would be actually our right answer for numbers. Is that number 15? Okay. Hold up. 15. Oh, 16. I'm sorry. Yep. So A should be the right answer there. Cool. All right. So we went through a lot today, a lot tonight. Went through a lot of questions. I hope that was helpful for you. I know tomorrow there's going to be more questions as you navigate. I would recommend getting there at 7:30. Get there and let's get going. Tell you what, I'll allow you to do this tomorrow. Yeah, okay. I'll tell you what. Here's what we're going to do, okay? Here's what I want you to do. If you tonight, Lindsay, don't say that. Don't say that at all. If you tonight if you want to come to tomorrow's help session in the morning, if you're coming to class, it doesn't count. But if you're coming to the help session in the morning, at 7:30. What I would recommend is get there early, 7:30, and then also if you text me in the group me what donut you want from Dunkin' Donuts, I'll get you a donut tomorrow. Cool? All right. So if you tell me what donut you want from Dunkin' Donuts, put it in the group me. I'll get donuts for y'all tomorrow morning. Okay. So if you want to, go right ahead. Lindsay, that was good. That was a good one. Okay. So yeah, so just put in the group me and we'll rock and roll. If you say, Coach, what would you recommend me to do tonight? Like you have a couple of extra minutes to study. What would you recommend? I would recommend trying to take some of these questions and go through them yourself. The answers are at the end, or they're obviously the multiple choice answers are in that link below. But I would go through that there. I would also, if you have a friend that is in AP Stats, or if you would like to, I would tonight literally walk through each of these and say, literally, this is what I would do. If I was a student, here's what I would do, okay? Some of you won't do this, which is fine, but I'm telling you it helps. I would literally get a white sheet of paper, copy paper, and what I would do is I would just literally put 7B concept list, okay? Perfect. And I would say, okay, I would literally put 1, and I would say, okay, statistic, parameter, sample, population, know how to apply these definitions. Okay. I would literally say, okay, what is a statistic? And I would just write this out. What's a population? A statistic goes with sample. Parameter goes with, I put these in out of order, but a parameter and a statistic are actual numbers. Right? I would write this out. Maybe I'll give myself like a little illustration, make one up, right? So like maybe a good example is like all GAC, own AirPods would be 75%. Population being GAC, all of GAC, 75% is my P. That's there. And I would literally write out each of these things in regards to this concept list. Don't ignore this. This part is huge. And then the last thing I would do is make sure you memorize tonight. Please make sure you memorize that list where I put the P-hat stuff here and the Muse over here. And then I talk about all these different categories. Make sure you know the categories and when to apply each, okay? That's what I would do as you're going through, okay? But if you want a donut tomorrow, put in the group me. I'll get you one. I'll get it there. I do love y'all. I really care about y'all. Team, you're going to do well. Again, proper preparation prevents poor performance. So prepare tonight, prepare, and know that I'm in your corner. Lindsay, don't know if I can. I might head out today on that note. Have a great night and be blessed. We'll see y'all. Bye.